Hello, my name's Hami Abdi, and today I'd like to talk to you about a thing I built that I'm calling Infinity Picture Grid. Here's the agenda for the presentation. We'll first start by briefly discussing the motivation to do this project in the first place. Then, to whet your appetite, we'll take a sneak peek at the core functionality of what I built, which is entirely front-end focused with the back-end counterpart mocked. Then, we'll dive a bit deeper and take a look at a few different subjects: placement, virtualization, responsiveness, and analytics. To wrap up, we'll discuss some future work. Many people have been showing interest in learning more about what I do for a profession. I figured that building something personal so that they have a concrete example would be helpful. Also, I thought that it'd be a good opportunity to challenge myself and have a lot of fun while doing it. Here's the sneak peek promised earlier. Now, let's dive a bit more into the details to cultivate a deeper appreciation for the project's output. First, I want to start by taking a closer look at the image placement. Images are placed in columns, prioritizing the least filled column. In case of a tie, they're added to the leftmost column. Here's an illustrative visualization. Here's a demonstration of the image placement in the application, with the application's configurations tweaked for demo purposes. Maintaining all images on the DOM while the user scrolls is naive. We can do better by only attaching to the DOM images that intersect the visual viewport, like so. We can do even better by including up to a buffer amount of items above and below each column. Here's how that would look conceptually with the buffer set to 2. Here's how it looks in the actual application. First, we scroll down far enough for the rightmost column, arbitrarily, to have the set maximum number of buffer items 3. Next, we observe that there are indeed 3 items above the visual viewport. We perform a similar check for the bottom. This time, additionally, we also make a mental note of the image corresponding to the last buffer item, a goat, so that we can do a sanity check. As we scroll down 3 items and see that the goat is indeed there as we expected, we also observe the column's content updating according to virtualization. Next, we do a similar thing for another column in the opposite direction. Changing gears, let's take a closer look at how the application accommodates different visual viewport widths and device pixel ratios, or DPR. I'm not going to discuss changes in height because the application doesn't do anything special aside from making sure it works as you'd intuitively expect. The grid centers equal width columns with an 8-pixel gap between each adjacent pair. It allocates a column width as follows, with the caveats to ensure that the column count never decreases as the visual viewport width increases. For visual viewports that have a width of less than 391 pixels, it allocates a width assuming that there will be exactly 2 columns. For visual viewports that are equal to or greater than 391 pixels, but less than 1,921 pixels, it allocates a width of 256 CSS or logical pixels unless it would imply a column count that's less than the maximum column count of the previous range, namely 2. In that case, it assumes 2 columns and allocates as much width as it can to them. For visual viewports that are equal to or greater than 1,921 pixels, it allocates a width of 512 CSS or logical pixels with a similar caveat as the previous range. In other words, if the implied column count is less than the maximum column count of the previous range, then we'd want to resort to using that column count and allocate the corresponding maximum amount of column width. For further details, I urge you to take a closer look at the function update grid column dimensions in the file grid.ts. Here's a demonstration of the above column count and width allocations for each of the ranges mentioned, in the order that they were introduced. Based on the allocated column width and the DPR, the grid determines a set of suitable resource URLs, ensuring the correct cropping and resolution. In front-end development, the part about ensuring the correct cropped version is downloaded is referred to as the art direction problem, and the part about ensuring the downloading of the correct resolution version is referred to as the resolution switching problem. An important note: in the case of this project, due to my limited capacity, I didn't actually construct different cropped versions of the original images. Instead, 2 versions that are intended for the same DPR but different sizes are just different proportionally scaled versions of each other. Notwithstanding, the code fully implements a solution to address both the art direction and resolution switching problems. Let's see how that looks in the application. The grid starts out with a 512 pixel width cropping of an arbitrary image with the standard size. As we update the visual viewport's width, we notice that the grid correctly switches to the 256 pixel width cropping of the image. Then, we reload the page without device mode so that we can examine a change in the DPR without a reload. We start off with a DPR of 2 that the grid expectedly associates with the 2x resolution. As we zoom in and thereby increase the DPR, the grid correctly switches to using a 3x resolution. Before moving away from this topic, I also wanted to highlight that advertisement texts are also responsive. Notice that when the image is larger than the text is simply centered. But when the image is smaller than the full text is left aligned and truncated with ellipsis. Here's a demonstration. Moving away from discussions around responsiveness, now I want to discuss the analytical features of this application. One neat thing that the application does is that it maintains a record of advertisements that the user has scrolled fully into view. This will help improve the user experience by ensuring users don't see the same advertisement excessively. Let's see how that looks. Another neat thing that the application does is that it maintains a record of how many times the user has seen the subsequent loading indicator, the one at the bottom of the grid. This helps developers fine-tune the number of images retrieved per batch and the debounce wait time for downward scroll handling. Once again, let's see this in action. The final neat analytical thing is that the application has code to automate measurements of the duration between the server receiving the initial page request and the grid's readiness to paint the initial batch. This helps the developer benchmark the initial rendering latency and ultimately helps them optimize it and quantify the improvement. Please refer to the code in grid.view and v.config MTS for how this is done. Furthermore, the code has simulated an optimization that the backend can do to help the aforementioned latency. The code to help this simulation is in index.html and initial render optimization.ts, with the former also containing documentation of the experimental results. Let's take a look at a demonstration of recording automated measurements for the optimized initial rendering. To wrap up, I just wanted to discuss a couple of things that can be done as enhancements to this project. First, the obvious one is to enhance the grid so that it accommodates other media types, say videos, not just pictures. Second, in the current version of the application, images are placed within columns, each with equal widths. It would be interesting to explore the fundamentally different approach of placing different width images on the page. Third, related to responsiveness, the current architecture chains asynchronous handling, such as the process of retrieving an image batch and placing it on the grid. Whenever the height, width, or DPR changes, we reinitialize the grid, but before doing so, we essentially wait for all the previous asynchronous operations of a stale grid height, width, and/or DPR. Furthermore, what's worse about this situation is that the stale operations reference the updated height, width, and/or DPR. It'd be nice if we optimized this. Also, here's a visualization of the problem. Notice the extra upcoming flickering. And that's all. Thank you, and I hope you've enjoyed this presentation. I'm also hoping that you have fun with the code.